Okay, so first thing that we need to understand is that Newton's second law is going to govern what happens here. Okay, there's going to be an unbalanced or net force that's going to cause this system to accelerate. Okay, we call it a system because this has more than one part. Okay, all the other questions we dealt with, the kind of simple Newton's second law questions, everything was all kind of tied up in one neat little package. Okay, there was one mass and it was being pushed by however many forces, and we could find the net force fairly easily. Okay, but in this case, we have two masses and they're separate, and different forces are acting on them. Right, but what we have to understand about a system is that the parts are connected. If they're not, it's not a system, it's two separate objects. Okay? But because these two objects are connected by a rope, their motion has to be similar. In fact, not just similar, but exactly the same. It is not possible for the 5-kilogram block to accelerate faster or slower than the 4-kilogram block, because the 5-kilogram block is pulling the 4-kilogram block. They have to move together. Right? It would be like if a truck pulling a trailer, okay, had different rates of acceleration. If the trailer had a different rate of acceleration than the truck, either they're coming apart or the trailer's running over the truck. Okay, which, I mean, can happen in a jackknife situation, but that's something different. Okay, but in a situation where the truck is pulling the trailer, it is impossible for the trailer to accelerate faster than the thing pulling it. Right? Everybody follow me there. Right? They would both, however, have forces acting on them. Okay? Friction would act on the truck, friction would act on the trailer. Right? There's an engine force that's directly working on the truck and indirectly working on the trailer, and so on. So we've got different objects, but they're all going to move, or in this case, accelerate at the same rate. So what we need to do is put all our forces on this diagram. Okay? So what forces are going to be important for the movement of this system? What's going to pull on the 5-kilogram mass? Gravity. Okay. All right, so the force of gravity is going to pull on the 5-kilogram mass. If you recall, we said the force of gravity is m times g. So we take the mass and we multiply by 9.81, the acceleration due to gravity. All right, so we'll have 49.05 newtons pulling on the 5-kilogram mass. Okay. The question also says that the friction on the table is 32 newtons. The 5-kilogram mass isn't touching the table, so that's not working on the 5-kilogram mass, it's working on the 4-kilogram mass. Right, but what we got to keep in mind here is the 4 and the 5 are connected. So now that I've got all the forces on there, can I simplify this diagram, simplify this system? How much mass is the net force going to have to move? 9 kilos. It has to move it all. Okay? Whatever the unbalanced amount of force is, it's pulling 9 kilograms worth of mass. All right? So that's the first thing we have to realize about a system. Okay? In a system, the net force acts on the total mass. Okay, so if you're here on Friday, you already wrote that down. Okay, if you weren't here Friday, you need to write that down because that's an important thing to know about systems. Okay, so the net force acts on the total mass. Okay, therefore, that's what 3 dots means. Okay, therefore, all masses accelerate at the same rate. Right? They all accelerate at the same rate, but do they all accelerate it in the same direction? Not always. Okay, I mean sometimes they do, but in this situation they most certainly don't. The 4-kilogram mass is going to move to the right, and the 5-kilogram mass is going to move downwards. Right? So a tricky way to ask this question wouldn't be to calculate the acceleration of the system. It would be calculate the acceleration of this mass. Okay? And people would mess up because instead of using 9 kilograms, they would use 4. Okay? Because they would forget that this is a system. and that the net force acts on the total mass. All right, so here's what we want to do. If we understand this, that means we can simplify this system to look like this. It's 9 kilograms worth of mass being pulled this way by 49.05 newtons and being pulled this way by 32 newtons. Okay? Effectively, that's what's going on in this system. There are two forces pulling on 9 kilograms worth of mass. All right, can I calculate the net force now? Okay. What are the two ways to calculate net force? Stephen, what's one of them? M times A. Okay. What's the other one, Davis? What would I do with these two numbers? Right, so I would find the vector sum of the forces, right. All right, those are the two ways to calculate net force: mass times acceleration and the vector sum of all forces. So right now, I can't use this way. I don't know what the acceleration is. I'm being asked to find that, right? But I can find the vector sum of all forces because I know the only two forces and they're opposite. All right, so F net is going to be 49.05 minus or plus negative, whichever way makes more sense to you. Okay, 32, so we should have 17.05 newtons. Okay, everybody all right with that? All right, can I calculate the acceleration of the system now? All right, so now I'm going to take m times a. Acceleration is going to be F net divided by m, so 17.05 newtons divided by 9 kilograms. Okay, so we got 1.89. Actually, we only have two significant figures here, so 1.9 meters per second squared. Okay, acceleration is a vector quantity, but I'm not putting a vector on that answer. Why not? Right, I calculated the acceleration of the system. And the system has two moving parts that are going in different directions. I cannot give a vector for the acceleration of the system because the parts are different. Okay, again, a more challenging way to ask that question would have been calculate the acceleration of the 4 kilogram mass, because a lot of people will forget that they want to divide by the total system mass, and they would forget to put a vector on it. Okay, if I asked for the 4 kilogram mass, then it would be 1.9 meters per second squared right, or toward the pulley, or something like that. Okay, everybody kind of follow there. So when we have a system that is more than one mass, right, the net force acts on all the mass, and all the masses accelerate at the same rate. Okay, those are the things we really have to remember about systems. Now, within a system sometimes, in a more complex system question than this, we might get forces acting on only one part and not be able to figure out the information for the whole system. But if I can find the acceleration of one part of the system, is that the acceleration of all parts? It is. That's the other thing we have to realize. Is if I can find it for one part, then I can extrapolate that or apply that to everything else in the system. Okay, I want you to think about that when you try this one. This one's a little tougher. Here's what we have to realize. The acceleration of the 40 kilogram block is the same as the entire system. Okay? The force pulling the system forwards is 150 newtons. The force pulling the system backwards is 120 newtons. They told us the total friction. So I can simplify this diagram right off the bat to say there's 100 kilograms being pulled this way by 150 newtons and this way by 120 newtons. Okay, that's all there is to it in terms of calculating the acceleration of any one of the blocks or both of the blocks. Okay, my net force in this situation is 30 newtons forwards. Okay, and if I divide that by the mass, okay, to get the acceleration, so I go F net over mass, that's going to be 30 newtons divided by 100 kilograms, then I'm going to get an acceleration of 0.3 meters per second squared forward. All right, and I can put a vector on it this time because both objects are moving forward. Okay, it's okay to put a vector on the whole system because the whole system's moving the same way. All right, now I want to find individual information. Okay, I found out the whole system. I know the acceleration of the 40 kilogram block is this, 0.3 meters per second squared. So now I should be able to calculate the tension in B. Okay, they tell me how much friction is acting on just the 40 kilogram block. All right, so I should be able to figure out, right, the acceleration there. Let me give you a few more minutes. Sorry, not the acceleration, the tension in cable B. All right, there are actually two ways to do this. One way using the 40 kilogram mass and one way using the 60 kilogram mass. They will both arrive at exactly the same answer. All right, let's start by doing this with the 40 kilogram mass. Okay, I'm just going to draw a free body diagram of the 40 kilogram mass. And this is the hardest part of the question. The math is easy. Okay? The hardest part of this question is recognizing what forces are acting on the 40 kilogram mass. All right. There's 150 newtons pulling it forwards. We know that from before. Okay? They told us that that's how much forward force there was. We know that there is 48 newtons worth of friction pulling back on the 40 kilogram mass. What else is pulling on the 40 kilogram mass? The block behind it. How is the block behind it pulling on it? They're attached by a rope. So the other force acting on the 40 kilogram mass is the tension in rope B. Okay? If you think about it like this, if I come over here and I pick up this desk and I just pull it, okay, it pulls pretty easily. But if it was tied to the desk behind it, would I have to pull harder? It would, and there'd be tension in whatever rope I was using to connect the two desks. Okay, it's naturally going to be harder. All right, so I need to find the tension in cable B. That's the missing force here. I can already calculate the net force acting on the 40 kilogram mass because I know its mass, and I already calculated its acceleration. That's the second hardest part of this, is realizing you can do that. You can calculate the net force on individual parts of the system as well as the whole system. All right, so the net force acting on the 40 kilogram mass is 40 times 0.3. Okay, so the net force is 12 newtons forward. Okay, the other way to calculate net force is the vector sum of all the forces. So that would be the force of friction plus the tension plus the applied force. Okay, that's the 150 newtons. The one I don't know is this one. So I'm going to subtract the other ones over to the other side. So I'm going to have F net minus the applied force minus the force of friction equals the tension in cable B. And I have to make sure I put the right signs on these because some of them are backwards and some of them are forwards. All right, F net is forwards, so that's going to be positive 12. Minus the applied force, which is also forwards, 150. Minus friction, which is backwards, so minus negative 48 equals T. All right, so I've got 12 minus 150 minus negative 48. All right, so the tension in cable B is 90 newtons backwards. Everybody follow me there? All right, all I've done, okay, is a question that we would have done easily last week. Right, there's 3 collinear forces acting on this mass, and I had to find the one I didn't know. Okay, we did a whole bunch like that. But because it's suddenly part of a bigger system, we forget. are basic skills. Okay, we got to remember that those fundamentals we learned last week are still part of tougher questions. Okay, I warned you that Newton's second law gets really intuitive. Right? It becomes a matter of visualizing all the forces acting in any given situation and being able to put them on a free body diagram and then apply the easier stuff, sum of all forces and m times a. Okay, those two things are mathematically not difficult. Okay, it's figuring out what ones are involved in those two things that can be difficult. Okay, so everyone follow what we did there. So that's, sorry, we said that was 90 newtons and that was negative, so backwards. Now, the other way to have done this would have been to use the 60 kilogram block. It's actually a quicker free body diagram because there's only two forces acting on the 60 kilogram block, the tension in cable B going forwards and what going backwards? Friction. Okay, now we know the total friction is 120 newtons, and we know that 48 of that is acting on this one, so how much is left? 72 newtons, right? So we could have easily just done this as well. Okay, it's kind of whichever way makes sense to you. I take my 60 kilogram mass. I don't know that force, it's the tension in cable B, and I know this force here is 72 newtons. I can calculate the net force because it's mass times acceleration. Okay, so 60 times 0.3, that's 20, isn't it? I didn't really just punch that in. No, it's 18, sorry. Okay. 18 newtons. Okay, so we got 18 newtons there, and now we can do the other way. F net equals force of friction plus tension. So tension equals F net minus the force of friction. 18 newtons minus negative, what did we say, it was 72. Okay, so 90 newtons. Okay, this time it's positive though, because from the 60 kilogram box's point of view, that's 60 newtons going forwards. From the 40 kilogram box's point of view, it was 60 newtons pulling backwards. Or sorry, 90 newtons pulling backwards. Okay, everybody all right with that? Okay. I'm going to go over one more type of question that we went over on Friday, and then we're going to have you just do some practice here. Okay, here's the situation I've got. I've got this is like, if you ever been and watched like a Stampeders game or something like that, they got that big speaker hanging down in the middle of the field on cables. Okay, so this is a big speaker being hung by only two cables this time, right? They're attached to walls, okay? And the attachment points to those walls create 40-degree angles with the vertical, all right? There's 100 degrees in between them. I want you to calculate the tension in each cable. Okay, how much tension is in each one of these cables, A and B? I'll tell you right now as a hint, they're the same. If you can calculate the tension in one of them, you know the tension in the other. Okay. Think about what forces are acting here, okay, how you calculate them. This type of question is what we call a static question. Static because it's not changing. The speaker is not accelerating. All right, so think about that. I'm going to give you a few minutes, see if you can figure it out. There's so little calculating in this question that realistically, if you knew how to attack it, you'd be done. Okay, there's that little calculating in here. The thing we have to realize about this question is the speaker's not moving. If the speaker's not moving, the acceleration is, what's the net force then? 0. All right, so there's no net force. That means all the forces pulling on the speaker cancel. They all add up to 0. So what force is pulling down on the speaker? gravity. All right, so calculate the force of gravity on the speaker. We just go 120 times 9.81. So we've got 1177.2 newtons. Okay. Now I need to isolate the two cables. Okay, because I can't solve for them both at the same time. They're pulling in different directions. So what I need to do is recognize that each cable is supporting how much of this 1177.2? Half of it. All right, so if I divide that number in half, I now know the vertical component for each cable, 588.6 newtons. Okay, because each cable is holding half the weight, but weight is straight down. So it's the vertical component of each cable. Is everyone with me that far? Okay, you can only fight gravity by pulling straight up. Okay, the other side of the triangle for each cable is them pulling against each other. Right, now I don't need that right now. I already have enough information to find the tension in cable A because I have one side and an angle. Right, so I'm looking for the hypotenuse and I have the adjacent side. So the cos of 40 degrees in this case equals 588.6 over the hypotenuse, which is what I'm looking for. Right, I'm looking for the tension in the cable. So to find that, I'm just going to go 588.6 divided by the cos of 40. I'm just rearranging that formula. Okay, so the tension in each cable, and we only have two significant figures here, is 7.7 times 10 to the 2 newtons. Okay, and that would be 40 degrees from vertical. Okay, pulling at 40 degrees from vertical. All right, everybody follow what I did there? Okay, static questions. Okay, static questions can be a bit tricky if we don't recognize that all the forces add up to 0. Okay, because then we have trouble calculating our net force. We have to recognize that our net force is 0 because there's no way to calculate it. Right. Okay, what I want you guys working on now is some of the questions from the digital workbook. So I'll call that up here. Okay, and I want you guys to start on, let's say, question 6. Question 6 is way easier than any of the questions we did today. Okay, in fact, most of the questions on this sheet until you get to about 15 or so, okay, are quite a bit easier than what we did today. You do have an elevator question. Okay, you're going to get a couple of kind of friction questions and things like that. Okay, and as you get further down, I'm going to have to teach you how to do another kind. Hopefully we'll get to that today. We can talk about inclined planes and how they work. Okay, so number 6 is one of these questions where you start out with a kinematics formula first. Okay, we know that the car, we know its mass, okay, is 1.08 times 10 to the 3 kilograms, okay, and we know that it accelerates from rest for 12 seconds. Okay, during this time, it travels 132 meters north. All right, what's the net force acting on the car? Can I calculate the acceleration with these 3 numbers? Right, I can use this formula, D equals VI times T plus 1/2 AT squared. Right, I have that much information. All right, so because VI is 0, I can just get rid of that, and I can say I can manipulate for A. So I'm going to divide both sides by half of T squared, and that'll give me the acceleration I'm going to need. All right, so the acceleration will be 132 divided by 1/2 times 12 squared. Oh. Oh, I better put that in brackets or it's not going to do it in the right order. Okay, so I've got an acceleration of 1.83 meters per second squared. Now I can go back and do this. The net force equals mass times acceleration, right? I've got the acceleration. They told me the mass already. If I multiply those two numbers together, okay, I should get 1.98 times 10 to the 3 newtons north. Okay, I know it's north because they told me the displacement was north. Yeah? Okay. Any other ones giving us trouble? Okay, don't be afraid to ask, guys. Okay, next type of question we need to look at is the inclined plane. Okay, the inclined plane is the simplest machine. It makes work easier. Doesn't make less work. Makes work easier. Okay, how does it make work easier? Right, you can get a certain mass to the same height as lifting it by using less force. The trade-off is you use less force over a longer distance. Okay, you're not doing less work because work's force times distance. Okay, but it's easier to do it because you can do the job with less force. Okay, in fact, you may not be able to do the job if you have to lift it directly. You may not have enough or not be able to exert enough force to do it that way. Okay, with an inclined plane, it is possible. All right, I mean, it's how the Egyptians built the pyramids. Right, they didn't have help from aliens. Okay, they had big ramps made of sand and millions of people willing to help. All right. Well, no, actually the research now says that it was actually Egyptians that were helping and that they took pride in building the monuments to the pharaohs, not millions of slaves, as much as was thought before, because the timeline isn't right to have had the slaves there. Yeah. Anyway, that's what I last read and heard. Anyway. Okay, so here's what we've got. If I put something on a ramp, okay, if the ramp is frictionless, what's the object going to do? It's going to slide down the ramp. Even if it's not frictionless, if the ramp is steep enough, the object may slide down the ramp. Okay, why does it slide down the ramp? Gravity. That's what we all say. And to an extent, that's true, but it's not entirely true. Because gravity pulls which way? Down. Straight down, not down a ramp. A different force pulls down the ramp. Okay, so if I'm drawing a free body diagram for this block, okay, I'm going to have gravity going straight down. And in this case, that force of gravity will be 98.1 newtons. Everyone okay with that? Okay, the other force, if this is a frictionless ramp, that would be acting on the 10 kilogram block would be the force of the ramp. Okay, remember how we were talking about if you push on something, it pushes back? Okay, we hadn't gotten into that too much, but anytime you set something on a surface, the surface has to support it. Okay, but because this surface is angled, that normal force isn't equal to gravity anymore. It's less than gravity. Right? If this was a level surface, you set something on there. Apparently it's not all that level. Okay, if I set something on there, the forces are equal. Okay, the force of gravity is pulling down on the marker, the force of the desk is pushing up on the marker, and the marker doesn't move. Okay, but if it's angled, the forces aren't balanced anymore. Okay, because the normal force pushes directly out. Okay, so it'll be a little bit less. So what I essentially do is I draw this as a vector diagram. So I take this force here and I move it to there. Now I made it too long. I didn't reflect it. It should be shorter. Okay, so I've got them now drawn tail to head. I've got my normal force here. Okay, and I've got my force of gravity here on the head of the first. That means that my resultant is right here. What do you notice about this arrow and the plane? Yeah, they're parallel. Okay, they're parallel. They both point the same direction. That's why we call this force F parallel. F with two parallel little lines. Okay, it is the net force of gravity and the surface of the plane, what they add up to. Right? If there was friction, then I would draw the friction kind of like right here, backwards, and my net force would be a little smaller. Everybody fine? Follow me there? Okay. All right, so anyway, we've got now this F parallel. So what we usually just do is we kind of just draw F parallel right on here, kind of simplifying the diagram a bit. All right. If this line here is parallel to the plane, how big is this angle? "30 degrees. They're similar triangles. Okay? They have to be. Their ratios are similar. Okay, so this is a 30-degree angle. Whenever you draw that internal triangle, okay, that vector diagram, the angle between the normal force and the force of gravity is the angle of the ramp. That's how much they're different. Okay? If it was flat, there'd be no difference and they would be equal. But the more I tilt the ramp, the greater the difference between the two of them, until I don't have a ramp, I have a cliff. Okay? Then there's no normal force and I don't have an F parallel, I'm just falling. Everybody kind of follow me there? Okay. So if I know the hypotenuse of this triangle is gravity and it's 98.1, can I figure out how much of that 98.1 is acting down the plane? Okay? Just becomes a vector calculation. All right, so it'll be half of that. It'll be sine of 30 times 98.1. So F parallel will be 49.05 newtons. And now I could calculate the acceleration of the box down the ramp. That would be the only force because there was no friction in this question. All right, so we have to remember about all inclined planes is this little triangle here. All inclined planes use exactly the same internal triangle. Gravity is the hypotenuse, normal force is the adjacent side, F parallel is the opposite side. Okay. Anybody need that diagram anymore? If you didn't write it down, you should. So I'll leave it up there for a minute because now a lot of people want to write it down. Okay, so this question has two tricks in it. First off, it tells me that the box is in newtons. So what is this for the box? Mass or weight? Weight. And weight is which force? The force of gravity. So it's telling me that Fg is 340 newtons. I should be able to calculate mass if I recognize that. So it's something to watch for because very often this happens. In a Newton's second law question, they just say the box is this many newtons, and you have to recognize that's not mass, that's force of gravity. Okay. The second thing is that it is sliding down the ramp at a constant velocity. That tells you something else. Okay. Okay, I'm just going to put the picture on here, okay, in case you guys are kind of stuck at that point. All right, so we know it's a 30-degree incline. We have a box that is 340 newtons. All right, so I'm just going to quickly calculate what the mass of that is. Okay, so it's 34.66 kilograms. Not that I'm really going to need that number, but I just like to have it in my free body diagram. Okay, there's an applied force pushing up the ramp. We're told that in the question, but we're not told how big it is. Okay, sorry, we are told how big it is. It's 200 newtons. Pulling down the ramp are two forces. F parallel, that we talked about just a minute ago, and friction. How do I know friction's acting down and not up? Right, friction always opposes. If the box is going up the ramp, friction's going down the ramp. If the box is sliding down the ramp, friction's acting up the ramp. Friction always opposes. So whatever direction the object is going, friction goes the other way. Okay, so those are the forces acting on the box. Now, gravity is there as well. Okay, we're told that. Okay, that might help me calculate some of the other forces. So, can I calculate F parallel? Right, this is what we did on the last one. All right, we said that there's this triangle in here, okay, where this side's F normal, but we don't need that for this question, and this side here is F parallel, and the angle inside this triangle is the same as the angle of the ramp. So I should be able to calculate F parallel. It's going to be the sine of 30 times 340, which should be 170 newtons. Everyone okay with that? Yeah? Okay, so F parallel is 170 newtons. All right, I still don't know the force of friction, but that's what the question's asking me for. What crucial piece of information do I need to use now in order to calculate the force of friction? The object is being pushed up the hill at a constant velocity. What is it not doing? What's the net force? 0. Okay, it's not accelerating. If it's not accelerating, the net force is 0. That means these three forces add up to 0. So I've got 200 up, I've got to have 200 newtons down. That means friction is how many newtons? 30. Okay, everybody follow me there. If it's going to add up to 0, then I've got to have the same amount of force down the ramp as I have up the ramp. Friction is 30 newtons. Okay, nothing really mathematically difficult, but again, there's an intuitive leap that has to happen in that question. Okay, we've got to recognize what constant velocity means. Okay, tomorrow's Tuesday, so you have a quiz. I will post it later on this afternoon. Nothing like that yet, but there'll definitely be 2 Newton's second law problems for you to do. Okay.